Yeah, welcome to my talk, Caching the Trie. My name is Bastian. I'm a co-developer at Parity Technologies, and I directly want to get to my agenda. So today I want to talk about, first, what I want to talk about, then why I'm talking about caching and why do we need that, and then how do we implement it in Substrate. So let's directly start with the what. So I first want to give you an overview of like how the state access works in Substrate. I will not talk about in this chapter about caching at all, just like how you access the state in Substrate. So let's get started. I have here this what I call like a state access diagram. It's like four layers that you find in Substrate. We start with the runtime layer, and in your runtime you do like a storage get call and say, please give me for the key hello the value. So after you're in the runtime, so the next step is then the what we call the state layer. When you're in Substrate, when you're doing like any kind of runtime call, any kind of you want to get some storage value or whatever, you always do it in like for a certain state, and the state is always attached to a block in Substrate, and each block in Substrate has these what we call storage root, and the storage root defines like the state view. So like when you're importing a block, by import I mean like executing all the transactions and the block is finished, you end up with a certain view on the state that defines like how the state looks like for your particular block. And the state is defined then by the storage root. So what we're then doing is like here on the state layer, we're taking our get call, so we have our get call with our hello key and augmented with the storage root. This storage, and this call is then pushed down to what I call here the Trie layer. And on the Trie layer, we will operate on these Trie nodes. And each Trie node has like a unique hash assigned. It's like the hash over this node. And this Trie layer now works in the following way. In the following way, you have the hash, and then go to the database and tell the database, can you please give me the value for this hash? Then you decode it, and you get your node. In our case here, this node has like part of the key h assigned. So let's take a look on how this node is composed. First thing here, for the simplicity of this call, it's abstracted. So like what I'm talking here is like it shows you like an overview how it works, but not in complete detail how the actual implementation is working of the Trie. But each key, each node, each Trie node has like has parts of the key assigned. In our case here, like h, and then you have like, for the case as you have like a Patricia 16 tree in Substrate, you have like you can have 16 possible child nodes, and each of these nodes also has like a hash attached. And what we're then doing is like as we want to get the value for our key hello, what we're then doing, we're starting to traverse the Trie. So next thing is, okay, what's the next node? We get the hash, go to the database again, we get our next node, see, okay, it contains EEL, next node, and LO. So like that's then the way from the runtime to our to our state, to our Trie layer, getting the data from the database, and then we end up like at our LO node here with the value and push it back to the runtime. Then it gets back. Okay, that was now like this broad overview I wanted to give you to what we're talking about, or what I want to talk about here. And now let's get started with the why. So why do we need a cache? And yeah, I mean, it's not so complicated, the question, but yeah, why? And why do we want to have like why do we want to cache the trie? And yeah, what does it mean in some sense? To explain you why we want to have a cache, let's go back to our state access overview here. And what we have done is like we benchmarked from the runtime down to the LO node back to the runtime. So we benchmarked this entire call, and it showed that it took like 4,400 nanoseconds. And that's quite a lot. Because what it means is like for every for every key accessor you're doing, like when you're building a block or you're importing a block, every time you're accessing like the balance, account data, or anything, it would take like 4,400 nanoseconds to get this value. I mean, you're then asking, okay, 4,400 nanoseconds, is it really that much? And or is it, yeah. The point here is like, and why do I know that it's not good? So I can tell you there was already a cache, and it was called like state cache. So this state cache, let's get to our overview here again. The state cache was sitting directly below our runtime. So every call, like every time you want to get some data from the state, the first thing you were hitting was this cache. So when your data was already in this kind of cache, it could be directly pushed back to the runtime. And if you benchmark it, it takes 386 nanoseconds. So that's 11 times faster key access. So this 11 times faster means you can put like 11 times more like key access into your block, like which in the end means more transactions, complex operations, and all these kind of things. But now you may be asking, when we already had a cache, why do we need like some kind of new cache, or yeah, what's the problem with this? So, and the point is like there were not multiple, but two main problems with this cache. First, the eviction logic was really complicated, and the second problem was that it wasn't working for collators. So that means for collators, you needed to go every time, like no caching at all, go every time to the database when building a block. So first to our why is the eviction logic so complicated? Our state cache, the state cache was really simple. It was like a key value store, like a hash map. So you have a key, then you have your value. I mean, it looks, if you just see it here, it looks really simple. But the problem arises when you have multiple blocks. Like for example, in our example here, we have like 3 blocks, all with the block number 10, and we import all of them at the same height, so it's the same block number. But each of these blocks sets the x value to a different, the x key to a different value. And now you want to build a new block on our middle block here, our block 11, and then is the question, which is the correct value? In our case here, it was really with the state cache, it was complicated because the state cache was like tracking all these forks, tracking reorgs, like new best block, all this kind of information were tracked in the state cache, and in this cache, they needed to, okay, for example, we first imported the left block, then the middle block, and then the cache needed to, the cache needed to know, okay, which is now the correct value here, which made the logic really complicated. I mean, all this stuff worked for Polkadot for quite some time without any problems. But as we launched Parachains, we were getting reports of issues. The problem here, like also these cache issues, it's not telling you, hey, I'm a cache issue. It's more subtle changes. So for example, relative easy is like a storage would mismatch. So what happened is like you were, for example, importing block 11, and instead of taking x as 8, you were returning x equals 5. And so your storage root in the end was different. You were thinking, okay, storage was mismatched. But there was also like a lot of other errors that were really not that easy to diagnose. And the problem is also like, as it is a cache, the moment you turn off your the node and restart, the cache is flushed, and you cannot debug it anymore. So it's like it was really hard to debug this kind of cache issues. So at some point, this was one of the reasons where we said, okay, or we gave up and said we need to have something new for that. But before that, I want to get into why didn't it work for collators? When a collator is building a block, it needs to record all the storage access and put it into this what we call storage proof that is then sent alongside the proof of validity to the relay chain, so that it can be validated. And this recording works in the way that we each time we access a Trie node, we put it to the side and say, okay, this Trie node this Trie node was accessed, this Trie node, and this Trie node. In our case here, we would say, okay, we access the H, the EL, and the LO Trie nodes, all of them. But now, if you remember, with the state cache was actually sitting on top of it. So it would intercept all these calls. Like, for example, assume like that our hello key was cached in the state cache, and we would return it to the runtime. Our recorder that sits on this Trie layer would never see that it needs to record the H, the EL, and the LO nodes. So that was the reason why the state cache was then all the time disabled for collators, which made, as I said, like the performance then was like 11 times slower as you could have get with the state cache. So that was now my, that was now the overview of why we have these, why we have the state cache, and or why we need the state cache. Oh, sorry, not the state cache. Sorry. Why we need these? Why we want to have like a different kind of cache? Why we want to have these Trie cache? In the next, I want to get into the how. So, like, how did we implement this Trie cache? Before we start with that, we had these requirements. First requirement was that the caching is fast. So, what does it mean caching is fast? I mean, it's relatively simple. We have a benchmark. So we already run our benchmark with for our state cache. So we could use our benchmark, or like we could implement something new, run the benchmark again, and then compare the bare numbers against each other. So that's relatively simple to find out if we are fast. Then we wanted to have that caching also works on collators, because like if it works on collators, you could put more transactions, or a Parachain can put more transactions into a block, and so you use your block space much better. And we want to have like a simple eviction logic. The point here is like, as I said, like if there are bugs, if we have problems or whatever, when we need to debug it, it's better to have easier code, to stay sane and to have a better life. Okay, we started with like a relative simple implementation. The idea came from one of my colleagues, Emmerich. He said we could like put a cache directly above the database and below the Trie. So instead of going to the database, fetching the data, decoding it, and then having our node, we would go to this database layer, get the data, decode it. So it should be much faster, because like the database if you're accessing the database, in worst case you're going to your disk, because that's where your data is stored. And if you can keep it in memory, it should be faster. So yeah, for sure we benchmarked this. And our benchmarking was showing that we're still like 8.8 times slower than our state cache, which is not good or not acceptable for what we want to achieve here, because like the access without, or like accessing the state without the cache was 11 times slower, and yeah, so 8.8 times slower is not good enough for what we want to achieve. The good point here was that we already like could fulfill our other two requirements. The caching would work on collators. As I just showed you, we were like below our Trie layer. That would mean like we could record all the accesses to the nodes and build our storage proof. For the eviction logic would also be extremely simple. Because, as I said, like each node has a unique hash, and as the hash is built by hashing the node itself, the moment you change one bit, you get a different hash. It's quite simple. Like there cannot be there cannot be this problems of returning wrong data, as you had with the state cache, because the keys are unique per node. Now the question is, now the question was like, why is it so slow? So let's recap. We have our the database access is cached. The only two things we're still doing that the state cache was not doing is we are traversing the trie. So that means like, as I saw, we're starting with a root node and then going down until we find our node that contains the data. And we were also like decoding the trie nodes on every access. So what does it mean? So for example, if we access our hello key twice, like from the runtime, you access it once and then you access it a second time. Each time you do that, you need to decode all the trie nodes that are in between. Like you need to decode in our case here, our H node, our EL node, and our LO node. So like every time, so that 6 times you would decode the same nodes. I mean, the intuition already tells you that maybe decoding on every time is slow. So we took out like our profiler and run it against the profiler, and we found out that actually this decoding of the nodes was killing our performance. So what we were doing then, or like we came up with the second iteration of this trie cache, and we started to cache the trie nodes. So what does it mean? If we go back here, go back to our nice diagram here again, we see here that we, like, as I already explained, like H, EL, LO, these 3 nodes, we get them from the database and decode them on the fly. Instead of doing that, we have a cache here. So instead of going to the database then, we go to this cache and tell this cache, hey, can you please give me the node that is associated to the following hash? And then the cache can give you back the node. If it doesn't have the node, it goes to the database, decodes it, cache it, and gives you back the cached result. So we were like, we have done what we have done before. We were running our benchmark. Our benchmark revealed, okay, we are still 3 times slower. Still not in the range what we wanted to achieve. The good thing is, again, like that our other 2 requirements are still like fulfilled. We are still iterating, we're still traversing the trie, so we can record all the accesses. Parachains are still working perfectly, or the collators with this cache. The eviction logic still extremely or quite simple, because unique hash, 1 node, different hash, different node. Totally simple. So the question was, no, why is it so slow? So why is it still so slow? And what you can do here is like you can just compare like our lovely big O notation. With the state cache, you have like a O1 access, and for the trie cache, as you're traversing, as you need to traverse the trie, you have like always O log n, or in average. Yeah, I mean, Okay, so like yeah, that's the problem that we are having here. Why it's still so slow? So how do we solve that? So in our third iteration of this implementation, what we have done is like we came up with 2 caches. I mean, when you can have 1 cache, 2 caches are better. So instead of just having our node cache here, that I already explained, we also added like what we call a value cache. This value cache sits in the trie layer, but it sits on, as you can see, it sits a little bit on top of the trie. So it works in a similar way as the as our state cache. So like a request comes in, and if the value is there, you can return it directly. Otherwise, you need to go to the trie and start traversing it. The good thing was that our benchmarks were really good. Like it showed that we're like in an average to 1.4 times slower than our state cache implementation. That was like the range where we then stopped optimizing. I mean, we were playing around with some like parameters, and like you can probably still bring it down a little bit, because like yeah, a lot of stuff depends on how or in detail how it's implemented. But we were doing like also like real world benchmarks by using like importing blocks or syncing the chain, and we were already like on this, like syncing the chain was as fast as with our state cache, because we are probably already like bound by other factors and not by I/O anymore at this point. To our other 2 requirements here is the cache and the recorder are like aware of each other. Like they're both in the same layer. They can talk to each other. The caching still works on collators. I will explain that in a moment. And to our eviction logic for the node cache, simple. We still have our unique cache for the node. For the value cache, it's a little bit more complicated. I mean, in the state cache, we had this problem like you can have 1 key that is written by multiple blocks, every time the same key, and then you have a different value. Here you can still have the same property, but we want to have unique keys to ensure that like we don't have these cases of where we return wrong data. So what we're doing then in our cache is like we are prepending the key with the storage root, because the storage root, same storage root, same state view. So that means like, yeah, if you access a key for the same storage root, it should always return you the same value. Otherwise, there's a bug somewhere. So that's the way we solve the problem here for our value cache, to have like unique keys, which solves our third requirement. And now to the how does this cache or like this value cache works together with the node cache and with the recorder. So here I have like the overview of like we get our get call here, and then the trick what we're doing here is like when we have a recorder set or like we want to record, what we're doing here is like we are then asking the recorder, do you already have recorded like all the trie nodes that are required to access the following key? And if the recorder tells us yes, then we can just ask the value cache to return the value, which should already, I mean, if the recorder already has seen the trie nodes, the value cache should also already know the value and should return it. And if the recorder still not has seen these trie nodes, we need to still traverse the trie and ask the node cache. The point here is like, you know, maybe think, but now we are like maybe yes, then worse again as our like state cache. But if we remember, like the state cache wasn't working for collators at all. So it was like always like when we were recording, it was like 11 times slower. And now if we then use the node cache and need to iterate only for the first access our Trie, it's around maybe hopefully like 3 times slower, which is much better than 11 times slower. Okay. So yeah, that was now. Okay, no, it's okay. Yeah, okay, that was so most of my talk. I want to give a small recap here. So like what we've done is like we removed the state cache, we introduced this value and this Trie cache. We are still not as fast as the state cache. The state cache takes around 386 nanoseconds to access a key, and on our value Trie cache combination, it takes like 561 nanoseconds. But yeah, that's for what we currently have, it's fast enough. It should give like Parachains the possibility to have like to use their block space even better than before, because we can push more data into the Parachain blocks onto the relay chain validation, and yeah, that's it. Any questions? Or, yeah.
Thank you so much. A little bit of housekeeping. When you ask a question, put it as close to your mouth as possible, because it's a shitty mic. Otherwise, no one can hear you at all. Cool? You can give me some claps if you understand what I just said. All right, I love a good confirmation.
Opa. Hey, yeah, I'm a Kusama validator, so one question I have about that, like, about like 1/3 of the space on my hard drive goes for Parachains. So if it fixes like caching for collators, am I gonna have less space requirements in the future? Like, do I need to, like, is it possible I don't need to have so much space for Parachains in the future as a validator with the caching working?
What do you mean by space for the validator?
Like,
here. Okay, can. Okay.
Yeah, so question. So the question is like 1/3 of like my space as a validator goes for Parachains, and with like you said like it was broken for collators, the caching. Is this gonna change anything in that sense as a validator? Space consumption.
What space concerns as a validator? I mean, like you mean the POVs that you're storing?
Probably.
Yes. I mean, theoretically, like if you can push more transaction into the POV should get bigger, and then you need more space. That is your question. Like the POV is like like you said, you mean the data that the validator is storing for the Parachains 24 hours.
Yeah. That one.
Yes. That are essentially the blocks with the storage proof.
Okay.
So if you can push more transactions into a Parachain block, the Parachain block gets bigger. Also, the storage proof gets bigger because you access more keys, which makes the entire block bigger. So you need more space on your validator disk.
Okay. All right. Cool.
So, Costa.
Hi.
Hi.
Just got a quick question. Is that currently available? What version is that available from?
What?
Could you hear me?
Yeah, he says 32. No, it should be earlier. I think it's, I don't know. I think I merged it in August or something, August. So so it's already available on Polkadot. Sorry. And if you're using like 930 or something, that it's also available for Parachains.
Okay.
I mean, like, as we instructed everybody before, like to like all the Parachain operators to run with the state cache disabled. And if you're still doing that, the node will print at the beginning in warning saying this CLI option is not used anymore. Please remove it or whatever.
OK, thanks.
Let's say you want to iterate over a storage map in a block. What impact does the new caching have? I would imagine that just the prefix of the storage map is then value cached, but if you iterate over all the keys, you still have to traverse the trie, or is there some optimization going on?
Yes, you still have to traverse the trie. I mean, as I was working on it, I have seen like there's room for improvement. Sorry, I need to drink something. But yeah, I mean, so storage iterations are currently not like. I don't think that they're that much getting from that, but there could be ways where we could optimize it even for these kind of storage transactions or whatever to be faster. One of the main problems there is, for example, currently, when you're doing an iteration, you're always like restarting, because iteration is driven by the runtime. So like you're starting with the first key, then you're telling, OK, give me the next key. So you're starting again from 0, then you get the first, and then you get to the second key. Third time, again, you iterate over all these keys. So we could probably keep some kind of some state on the node to make that faster, so to continue where we stopped. Something like that.
Hi, awesome talk. So I was wondering, when is the cache really updated? So in particular, let's say I send a bunch of RPC queries like for raw keys, for let's say really old blocks. So will the cache update?
Currently, yes. But we want to change that, or like we want to a little bit. So like cache updates always happens like after the when you're doing like, for example, iterations or getting a key or whatever, you're having some kind of local cache which caches like your results locally. And if this scope is when you leave the scope, this cache is dropped and you update this global cache, which has a global cache view or whatever you want to call it. But we want to change it in a way that you can tell it, OK, I'm, for example, now in an on-chain, like, or you're importing a block, you're building a block, which is much more important than like any RPC thing or whatever, then it should be.
Yeah, I just basically wanted to ask about what you just said, that like building a blocks is more important than answering RPC queries. So if you updated the state cache after the RPC query, you could force the node into like invalidating the cache, replacing all the keys with all the data that will never be used by the block, and then slow down everything.
Yes.
Is the trie data structure held in memory or not?
Yeah, no, yes. Not whatever is your trie data structure. I mean, the nodes, yes.
OK, and when I tried implementing a trie, I had to use a box to get around the recursive type. How did you manage to get around recursive types in Rust?
With box.
Yeah, OK.
I mean, like each node cannot, like you, if you have like if a child node is like smaller than like your hash value, like your hash is like 32 bytes. If your node is smaller than 32 bytes, it's kept as an inline node in your outer node. So probably in real life use cases, you in maximum have only one inline node, maybe two or whatever, but not that many.
And how many nodes did you, how many child nodes did you have per node?
60. Yeah, 16. I mean, the 32 depends on you. If you have like, if your hash type is 64 bytes, then it's 64. It's just an optimization because like if your node is smaller, then like the 64, it doesn't make sense to put a hash there.